again, starting from first slide. Look, I get a pretty small group here, so this is just going to be really informal. I'm just going to talk about it.
Yeah.
We'll get out of here real quick. Again, this is a continuation. Last time I had an opportunity to speak here, I was just talking about how it is you would handle a portable executable if it's on disk. And if we don't remember the detail of that, effectively a portable executable, that is the name of the format that's used for Windows executable files. That's all. What's going to be a little different in this presentation, the last presentation we spoke a little bit to what it means to load one of these files into memory. But again, from a coding perspective, we only dealt with it on disk. In this series, we'll actually deal with coding for it while it's inside memory. We're actually going to use a mainstream memory forensic toolkit to be able to do that. So, you know, double the benefit. You guys could become contributors to one of the biggest memory forensic kits out there and used around the world. That being said, as always, anything I express here, it's my own views, and this reflects what we do in practice at my place of business. This is all private research. I think you guys have seen enough about me. Lots of stuff. Here's kind of the format. I'll kind of rehash what it looks like moving an executable from disk into memory, just conceptually what that looks like. We'll talk about from a kernel perspective, which is the operating system, how it is it manages those executables and they go into memory. We'll talk about some important data structures, specifically the process environment block. We'll talk about something called the virtual address descriptor tree, which is like really important to how memory is managed for a process. Then we'll start hitting on some programming basics effectively. Again, using volatility framework. Again, it's just a bit of a throwback. You know, on my right, your left, again, is maybe what the virtual addressing looks like. It's continuous. And the idea is that when, you know, one of these portable executables loads into memory, you know, again, those files expect for things to always be at the same location from an addressing perspective. But in reality, it's really hard to do that with with physical memory, because where the space is available could be all over the place. And so the operating system manages those nuances by translating every time an address is referenced to where it's really located at physically. Moving along. Again, this is the executive object layout for a process. And what's really key here, I just picked out some specific entries within that data structure. And the reason why I pick these out is, you know, in my day-to-day work, I do mostly forensics and analysis of malware. And so it just happens to be that these are the specific entries that are most useful in that line of work. I will show how it is you can look to see what other data items make up that structure, so you can see for yourself and maybe pick other things that are interesting to you if you choose to pursue this programmatically. With that being said, let's speak to what's on the board. So for the e-process data structure, now this is for Windows Server 2003. Again, I will show you how to see that for modern operating systems. For Windows Server 2003, which is what I have a memory image of, you know, I've picked out, again, create time. You can imagine when a process first loads into memory, that could be really important when we're trying to tell the story about what happened on a computer. I think I've said it in some other presentations, you know, computers are like little time capsules, everything is time-stamped, and that includes, again, things that load into memory. We also have exit time. Now, when a process exits memory, if you were to pull up Task Manager, you wouldn't see every process that ever left memory. But in the last presentation, I was talking about, like on disk, how there's these markers within the file that let you know that it really is a portable executable. And just to kind of put it in layman's terms, you know, if you were to, again, take a hex editor, look at a portable executable on disk, the very beginning of it always has the letters MZ. Well, when it comes to this eProcess data structure, before it, there's usually something called a pool header. And in this thing called a pool header, predominantly in Windows, you usually find the letters PROC. And because, again, you know, all these operating systems, anything that's loaded into memory has to conform to a set data structure. If you find that PROC and you read ahead, again, you should be able to find these other data structures, which includes, again, the items that I listed in front of you that would make up the eProcess portion of the data structure. Some other items that are kind of interesting is something called object table. In the object table, we find handles in order for once a process is loaded into memory. Let's say, I don't know, you were using notepad.exe, right? You loaded a text file into memory. In order to be able to interact with that file, the process has to open up another kind of executive object called a handle. And so again, for the eProcess structure, it tracks all those handles inside this object table that I identify here. Just to kind of speak to the columns, just so we're on the same page, again, we know it's 632 bytes in size, and this for the initial 2003, and then on the left is the exact hexadecimal offset of where it is you would see that particular data item if you're reading it. To the right, we again spell out what the data type is, what the primitive is, and then we try to create a little bit of context so that it's common and some context as far as what it means, again, if you're reading data there. And so, again, for object table, if you were reading this particular entry in the executive object layout, it's really just a pointer to where the table is. And then the table itself has a data structure called handle table. Now what's cool is when we get into the programming side, again, you're able to look up all these data structures natively with the Volatility Toolkit. And so it's really nothing you ever have to memorize. You just really need to know how to use that environment to help your development along if you're trying to, again, deal with these artifacts in memory. Again, physical bad root. Again, this is the actual name of the official name of the data structure that describes how the virtual address descriptor tree is set up, and this is the pointer to the beginning of that tree, the actual physical address in memory. And again, just remember, a process that's a file that is loaded in memory has become a process typically wouldn't have access to this data. This is typically only accessed by the kernel, so again, it can track those translations that need to be going on. Also, another item that will be of specific interest today, and is typically of interest if you're doing exploit development or incident response or forensics, is the process environment block. So that's what PEB represents, and that's definitely what I chose to handle programmically today, just to kind of dig into the content of it. And then there's usually some other, again, interesting stuff. You know, we can look at creation info, and that includes things like who actually started the process, what identity it opened under, things like that. And then finally, bad root. Again, this is just a reference to the table and the very top node in that tree, and I'll speak a little bit more in detail of that later in the presentation. Okay, I'm moving on to process environment block slide. Again, the process environment block is typically 560 bytes in size. What's interesting about it is, as an example, if you were a malware author, like one of the things you're interested in is, am I currently being debugged? Usually if you're in the business of reverse engineering or, again, incident response, you see a suspicious process. In order for you to access the content of that process, you have to put it in debug. And so, of course, the process itself can kind of self-defend by reading that all the time. Going, is somebody debugging me? Is somebody debugging me? So anyways, it's kind of an interesting field. That could also be indicative of other bad things going on if you're an incident responder. So if you know, some of your processes are being tagged as being debugged, I think it's a fair question. If it's not you who's doing the debugging, but you got the memory sample, well, what's really doing that? Again, LDR, that's just showing how different modules or libraries were loaded. Typically when we run anything on Windows operating system, there's like the code you write, but typically you're very dependent on the underlying operating system. And for this example, the Windows API. There's also process parameters. Again, that could be really interesting as well. Good example of that is, I don't know if you guys work with PowerShell in your day-to-day, but PowerShell is really interesting because you can call the executable and then literally pass it a really long single line command, which is all your code, and then it's running. And so sometimes looking at process parameters can be super relevant from an incident response perspective, even forensics. Moving along, and just so we have a little bit of continuity here, so we're going from the e-process data structure, and then I'm going into the process environment block. And again, digging a little bit further, these are the process parameters that I was referencing before here. And so from the process parameters, we can kind of see some other interesting things, which I will not deal with programmatically today, but I just want to point to how much statistical and management type information is being managed by the kernel. So again, if you are able to get a copy of memory, you can tell a really detailed story on what's going on. And so again, we can see what the standard input is, standard output, standard error. You guys are probably used to that from a programming perspective. We can see the current directory that it's running out of. A lot of time that can be a big giveaway. Like again, if you're a malware analyst and you're looking at a memory sample and you see, for instance, an SVC host, and it's not inside C Windows System 32, that's usually, again, just a quick giveaway, like, okay, this might be bad. That should never be anywhere else. And so, again, the thing that we do know as practitioners in the industry is that a lot of this information that we find here is typically really consistent when we look at things loaded in memory. And so, again, variability here could be an indication of bad. Or again, if you're up to no good, it could give you some indicators as far as where to go do your bad stuff. Also, we can see the DLL path, right? What's our primary path? We can see where the image was loaded from, which again is the portable executable of the file itself. The command line, again, I was describing that you could run, for instance, PowerShell.exe, and then I think it's like a -C, and then in parentheses, again, whatever your code is. And again, we can also see the environment. Typically, environmental variables can sometimes be maliciously modified, and that might be how the malware was able to load by placing itself, again, in a directory that's preferred when, say, looking for a DLL that it needs, and again, giving it the same name of a DLL that's widely used within the operating system. Just an example. Okay, along. Again, a little more here with process environment block, and specifically this is the LDR data. This is what I referenced earlier as far as what DLLs are loaded in memory. If you ever get out there on YouTube, there's a ton of presentations talking about how you find bad. And a lot of that's based on, again, if people are doing things like DLL injection or process hollowing, and there's just so many techniques you can get into. But the point is that this LDR data, what it exposes to you is 3 other lists that tell you when, in what order libraries were loaded, and then also in what order they're actually initialized, and then again, what order they're actually in memory from an addressing perspective. And again, it can be really useful to you because, again, a bad guy may decide to hide themselves in one of these lists, but hiding yourselves in all 3 lists might not be a good idea because your code may actually break. So, move along. Again, this is me. I'm just digging into those original items from the process data structure. This is the actual virtual address descriptor tree itself. And again, the only thing I'm pointing out here is that we have the address for the root node, the very top node, and then we also have another field that's kind of interesting from an analytical perspective, which is the depth of the tree, right? How many layers does it have? And so let me just get to it. Again, just a little more data. This again becomes interesting because earlier when I was talking about, like, for instance, the pool scanning, which again was looking for the PROC. We're scanning through memory. Again, it may give away where processes are located in memory. Well, again, all these objects have different pool tags, and so the same is true for the VAD, and that is something that you can would scan to look for. So that's kind of interesting. And what's more important here is that for every node inside the tree, it's typically this side, and this is kind of the common information. And what it tells you is, first off, who's to the left of the node that you're currently on, and who's to the right, which is going to be important later. And then finally, what is the starting address and what is the ending address of that particular node. This is kind of what a bad tree might look like. This is actually for one of the running processes that I picked up. I just want to say that the memory image that I use is from the National Institute of Standards. Everything I talk about today is actually inside of the slides, the notes themselves, and so you can go out there and you can download the same memory images I used to do this little bit of work and actually recreate it yourself, or again, getting something more creative than what I'm showing you right now. But what's kind of cool here is when we talk about, again, stuff being loaded into memory, let me just flip back real fast. Again, when we look here, we have our DLLs, right, loaded into memory. Again, we have our code that's loaded into memory, we have our data, we have our heaps and stacks and everything else. And so what's cool is that, again, using this forensic tool, and not that you need the forensic tool, because I'm going to show you how to program for this, you could identify where all the heaps, DLLs, and everything else are just climbing through this bad structure. And what's really interesting about the bad tree, you guys probably learned about this, I imagine maybe in your programming languages class or maybe object-oriented. It's a B tree. That's all it is. So if you're, if your starting memory space is larger than my own, you go to the right. If you're smaller, you go to the left. If something new comes in and it's bigger than me, again, it goes to the right. And we keep trying to balance. Again, smaller stuff always to the left, bigger stuff always to the right. And this feature, as far as the legend itself, where again, items in yellow show mapped files, so there's probably a handle and an object table that points to this particular space in memory, representing again where the file is, or again, red for the heaps. Again, those are all built-in features right now. And again, as a programmer, you don't even have to reinvent. You can actually take advantage of the code that's already there. Okay, moving on to framework developer basics. Here's kind of what it's down to. If I'm, there's some steps that that we're not talking about today, and that is how do you build a profile for the different operating systems which you may get a memory capture from. Rather, what we're starting off with is that we know there's some publicly accessible memory captures. There's already profiles pre-built for those, so we don't have to worry about getting into the detail and how it is you get the smallest level of information, which is the symbols that help you interpret the data inside the memory image. That's already been done for you. Rather, we're kind of moving up a layer. We're just trying to position ourselves to do coding for something that we know our framework, the volatility framework, can already handle. And so there's some key plugins that you typically want to run. And I'm excited to show you what that looks like. But effectively, in order, we'd want to do image info as our first plugin that we would execute if we did get a capture of memory. What image info does, it actually scans through memory and it tries to understand what operating system the memory came from. And that's really useful if you have an unknown image, or again, one of the challenges is that when you're telling this tool what profile to use or what operating system things came from, you also have to tell it, like, for instance, for Windows, what Civic Service Pack, what CPU architecture it came from. All this, it's a lot to go, oh yeah, it's all these things. So again, you have a plugin, you run it, it spits out some options. If you have a little bit of know-how, and you're like, oh, I know it's Windows Server 2003, again, you copy that profile, and now we run the next plugin to validate if it actually works. The next plugin that we run is called KDBG Scan. And what's interesting about KDBG Scan, specifically to volatility framework, is that this is the kernel debug table that it's looking for. And when you tell it what profile or what operating system and CPU and service pack and all that's associated with the memory image you have, again, that causes certain logic to be applied as it's reading through where this kernel debug table might be. And the result you get, if you're getting a good result, if you actually got the right setting for your profile, will actually tell you the number of processes, libraries loaded into memory, and a whole lot of other good information. If you don't get that back and it says, hey, error, couldn't find the profile, well, then you probably picked the wrong one. And the reason why I say it like that is that when we run image info, sometimes you'll get several operating systems that might be identified. And so you might just have to try a couple of them out before you get the one that's actually turning results, and then we can progress. Also, we use a plugin called Ball Shell. Ball Shell is useful because it's kind of like, so we're, what I'm worried with today is, again, showing how to program. But with volatility shell, it's kind of like, if your hex editor knew all the data structures that it might encounter. And so vol shell gives us just kind of a standard way to interface with memory with a very small subset of commands. And if you're ever trying to validate, are my tools working, or, oh, what was the name of that data structure, again, vol shell can help you get to that information very quickly. And what's really awesome is if we've done all these other steps, which again gives us the parameters we need to run Ball Shell in the context of the operating system where we actually got the image from, it'll correctly represent the right data structures. Like, you remember earlier when I was speaking, I kept saying, oh, this is from server 2003, this is from server 2003. That matters, every time the operating system changes, and this is real big with Windows 10, every time there's an update, there's always like some little small change to all those data structures, so it ends up breaking all your tools. So anyways, Ball Shell, really good stuff. I'll show you what it looks like in practice. And then finally, once we've cranked out some code, the last thing we probably want to run is our actual plugin to see what the output looks like. Again, I'll talk through what the most bare minimum thing is that you have to put in your code, again, leveraging this framework. As far as switches that are interesting, -H is just for help. What's cool about -H is that as we start to give volatility framework more information, like we actually figure out what operating system it came from, and CPU architecture and all that, every time we use -H, it continues to give us only output that's relevant to that specific operating system. And so that can be really helpful because out of the gate, volatility framework has a lot of features like, again, finding processes, and say from a Linux operating system or Mac OS X, and the point is those are not going to be applicable if we're looking at Windows. Okay, moving along. -F, again, that switch is important. This is a command line tool, so we have to use -F to say where our memory image is. And then -- plugins, once we get into writing our own code, our own plugins, we do have to say where it is we're putting our code at. And this way volatility knows that, hey, I'm not just going to read the plugins that come with the framework, but I'm also going to look at these custom plugins that the new plugin developers are writing. Again, -- profile, again, that's always followed by an equal sign, and then we're putting in, again, what operating system, service pack, CPU architecture, again, we're talking about Windows, and then finally --kdbg, typically that's followed by virtual address of where the kernel debug table is at. All this information is going to be provided back to you as we go through the order that I suggest to run the plugins in. Okay. And here's where I'm going to switch. Guys who are listening, so I'm not going to be able to show you what I'm doing from my development box. So feel free to grab that image and see if you can blow it up somehow for yourself. Again, I'm just using the help command in Vol Shell. If you're able to get there on your own, if you're not, hey, you're in Discord with me. We can always work on it together after the presentation's over with over the weekend. Okay, so to the left, I'm going to put up, again, the dev environment. One of the things that I like to do when I'm doing any kind of development, whether it's for, again, forensic tools that I'm going to use against maybe a disk image, or if I'm reversing malware, Again, I try to have several different shell windows open. Last time I presented, I spoke to PyCharm, and I was like, you know what? I felt like I spent more time in Linux, in different bash shells, and I was like, this time I'm only going PyCharm. So here's my PyCharm environment. Effectively, the way that I like to set up, kind of get to the point where I really just want to tell you a little bit about Vol shell. But typically, my tabs that I have open for code, I usually kind of put that off to the right, as you can see here. And then normally I open up a Python console, since we are Python programming, to write these plugins for Vol shell. And so normally I'll have the interpreter opened up. And what's great about that is that if you're like me, I'm always messing up my syntax. I'm like, oh, what did I set that variable to? And so being able to use the native help to kind of go back and like quiz myself, like, oh, what was that thing? What else can I do with a string? What else can I do with an integer? Again, that's what the interpreter is great for. And then finally, I have just a regular command shell window open. And I kind of keep two of them open, and I try to name them according to what their purpose is. And so one is, again, just for my plugin testing itself. And then my other window is for Vol shell. Now, what's on the screenshot that, again, I'm sure my Discord watchers are struggling with right now is that I'm just running a command called HH, and this is the native help. And effectively, I'm usually less zoomed in when it's me by myself. But effectively what we get when we run HH is me doing a lot of scrolling. I love it. Dock this. You know, you really can't do a presentation unless you have some failure. I guess that's what's expected. But affectionately, though, now you can kind of see, we are going to undock this to the window mode. There we go. Now we're going to blow that up and get back to the business of looking at this example. So when I run HH, again, this is what the Vol shell command prompt looks like. Here's me executing HH. It's just like any old function call if we're writing code. It's very comparable to Python interpreter as far as working within this environment. And immediately what we get back is all the different function calls that we can use from the current position we're in. Let me see if I run that one more time, if maybe it'll do a little better job with where the carriage returns are. But effectively, what we're presented with, again, is all of our options from a function call perspective. And the ones that are most meaningful to me is, I'm going to start from the bottom and kind of go up, is one, I can look at what my current context is. Typically, when you first run Vol shell, you typically come in as the system process, which is kind of the accounting process that Windows uses. So if I do SC, it's effectively telling me that. It's saying, hey, I'm sorry, for this one I actually switched. But typically the system process will have a PID of 4, not 1568, which is what I switched to before I came in here. And again, what's not so interesting about this process is that it's really there as a placeholder. It's not a real process. And so we're more worried with, again, files that load into memory. How do you deal with that programmatically? So typically I would end up switching context. So again, SC with parentheses allows me to see my current context, but really I would want to switch that. So I would use PS, which gives me a listing of all processes. Okay. Now again, for me, what's that command again, right? So I got my list. PS, it's CC, it's a little higher in the list. But the point is after running PS, we would use CC to change context, and now we could start asking questions based on being in the context of that particular process. What's key here is there's quite a few building blocks we went through, which again I will go through the other plugins that I showed running up to this moment. But the point is we continue to position ourselves that as we're using the tool, it keeps reducing and reducing and reducing what information it's returning to you based on, again, the context that we're using the tool in. All right, let me go back over here and we'll do some more with that here in just a minute. So HH, probably the key command that pretty much tells you the story. You just read the feedback you got on how to use the tool. Some other things that are really important from a developer perspective is there's some key libraries that we have to import. I just want to say, if you weren't familiar with this already, when we start doing imports in Python, really the very last word, if you will, is usually the actual name of the file that we're importing, and everything before that just represents a folder. And so if you ever want to go look at this code for yourself, again, if you go to the volatility project, again, you can quickly navigate to the exact location. So here I'm importing utils. So if I go to the volatility folder, again, this is just within GitHub. This was on your file system. The experience would be similar. You'd probably be doing a CD and then doing a directory listing. But the point is that immediately we're greeted with utils.py, and so you can always go look and see what the code looks like, rather than just accepting and I'm saying, hey, you probably need to import this particular library. So for our purposes, though, you will always need the utils imported, and the reason why is that this is when volatility framework is running. We've done all that prep work, running all the image, image info, KDVG scan, all the other information that we're getting from that. We're packing it into the command line. All that's stored within this utils class, within this utils object. And so we want to take advantage of that as a plugin writer to say, hey, the end user's already given us that information. Now we're just going to build on that. Okay. Also, volatility.plugins.common is really useful if we're going to be writing a plugin based on scanning. Just about all the talking I've done with respect to, again, files being loaded into memory, particularly executable kind of processes, again, has been very focused on this, discovering these processes in memory, even if they try to hide. And so, again, plugins.common is a good place to go if you're in the business of pool scanning, trying to find things in memory, because you can't trust the underlying data structures. Just to get this kind of out there, in order for volatility framework to recognize that you've actually written a plugin, you don't really have to import plugins.py. It's commands.py is the thing that you have to import. So it'd be volatility.command, and again, that would give you the appropriate class that you need to write a plugin that would be recognized by volatility. But for our purposes, because we're doing pool scanning, we're going to use this. Also, import OS. There are some OS commands that might be useful for you. It's always useful for me to use the OS library, so I typically bring that in. Also, in volatility, you have different kinds of renderers, and the only thing that is effectively volatility has many different outputs. One of them was like that bad tree. That's called dot notate. Dot is the output there. You can do HTML, XLS, CSV. There's so many. So anyways, these are renderers, and so I'm choosing to use tree grid, which I think creates a nice, pretty text kind of output that makes it more legible if you're only using the console and not trying to print it in some other file format. And then finally, for the plugin itself, typically when you're writing your plugin after you've done all these imports, typically we want to say, again, what our core classes or object that we're instantiating. In this example, we're extending this common plugin, and then again, the name of the class itself is going to be the name of your plugin, and the way that volatility knows to display information about your plugin depends on your use of comments. And so if you do the triple quote, anything you put in between the triple quote is what's presented whenever somebody does -H. Moving along, again, just to initialize the plugin, what's useful about this is that if you wanted to add additional options like command line switches, you definitely want to have an initialization function within your class. It is not mandatory. I do an example of not initializing anything. So it's unless you're going to extend the object that you're or the class that you're already building upon, this may not be necessary. Typically good to have. Other things that are useful, look, if you're doing unified output, that's good enough. I'll show you what that looks like, but I did want to point out also that the way volatility developers, I guess, did it back in the day was that they would actually choose the function call for the format that they wanted to display in. And so here I just call out render text because that prints to console. Also, there's another function that's needed. Again, these are required functions called calculate. And what's important about calculate is that we're taking, again, the memory that we have and we're doing something with it, and that returns an object called data. And data we can generically reference to in other places in our code. So if we want to render something, again, data has to exist, and that's only possible if we use this overloaded function called calculate. And then finally, you probably want to write some functions of your own, which I feel like we've spoke to ad nauseum. So it's def, and then your function name, colon, tab, and whatever your code's going to be. Moving along. Some other developer basics that might be interesting is the different V types. What's useful about the V types is, again, I use terminology here about overlays. Overlays is synonymous with profile, is synonymous with operating system plus service pack plus CPU architecture. Again, what we're taking advantage of is that somebody else already took the time to take all the symbols for the different operating systems and make it where we are able to see what's inside. Again, for our example, the eProcess data structure for Windows Server 2003. But you can check that out for yourself, what those look like. And just to show that very quickly, again, in volatility framework, let me point at something. You can see that it's import volatility .object, and .object, if I were to look at the code, it's just pointing back at plugins, and then it points at overlays, and then within overlays we can kind of have it broken down by the three base operating systems that volatility framework supports. And in here I could really search for any operating system, and so I'm just arbitrarily searching for Windows 7, and then I go to Service Pack 0, and I go to the 32-bit version of that. And if I open that up, I can search for, as an example, and there goes your entire eProcess data structure as it should look within the memory of that particular operating system at that particular service pack level running on that particular CPU architecture. But again, if we've done all the steps that I just suggested, if we can look back over on the development screen, natively we're able to now just query on those different data structures. The command that you would do is dt, okay? And that's up here, and you would just pass it the object type that you're interested in. And so we know for our purposes that we're interested in eProcess. So we just pass it that, and boom, there goes the data structure. Now again, you probably wouldn't have the text on your screen quite this large. I have it this big because you had concern people would be in that room. So I'm like super zoomed in. But the point is that again, from my slide, you can start to see some of the things I was talking about. You can see the process control block, the creation time, the exit time, et cetera, et cetera. And just to put this really into context, again, we can use DT to look at how the layout of that particular object is, but we can also look at that object in the context of a process. And so, again, I'm always HH, right? We look at the active processes, we switch our context with CC. Again, it's in help HH, and I'm choosing Notepad arbitrarily because it feels familiar. We get some information back that's kind of useful. Specifically, we get the virtual address for where e-process structure is. We can now query against that again using process. The address is equal to. Now all of a sudden, instead of just getting what the data structures are, now we start getting results, addresses, translations, right? And again, the nice thing is, because we're using volatility, instead of trying to roll our own, which we could roll our own at this point, I promise you, but just working with symbols, you would get, this is an integer as an example, right? The size of the data. But you wouldn't know just by saying it's an integer that really it's a date. But volatility also adds a little bit of flavor, and it goes, oh, well, I know this is supposed to be a date, and so it renders it in the Windows date format for you as an example, which again is an advantage you have if you just develop on top of an existing framework rather than inventing your own. Something else that's kind of cool is that, again, not all these items, like as an example, this is the process environment block, right? So that's the address of where it's located at, okay? We could take again, vol shell, we could tell it to recursively go through the eProcess data structure. Of course it wasn't going to work. Why should it? Again, helps your friend. What did I do? Capitalize it, I shouldn't have. DT, so we can see up here it shows that by default recursive is set to false. And so I don't know how to spell recursive. Apparently I'm missing an R in recursive. Spell check's not built into the console. So there it is. Now we went into bad root and we started digging and looking at what the bad tree looks like, right? By allowing recursive. We could also again go back to basics and just say, hey, what are these data structures, right? And again, as an example, we're zeroing in on process environment block. Anyways, it's underscore PEB, and I just want to point here, I ended up bolding this inside the slides. Again, I hate that I'm so, it's just because I'm so zoomed in. But we can see that the data type that's there, and so if we wanted to just query on that particular data type, again, we have to get the name right. So this is just like when I was using PT to look at when I actually process, I would do PT in parentheses underscore PEB as it was just shown above. Now I can query and then see all the data structures there. Now I know the address of that, and so I can actually query it for the process and see what's inside the PEB. Okay. All right, so back to presentation. Lots of fun stuff. Okay, and then finally, for again the programming example I'm going to show today, I'm using pool scan. So I end up importing pool scan because I don't want to invent my own pool scanner. Again, they already have one. They already know how to pull up the V types. I'll say, hey, do a pool scan, and then look for eProcess type. That's what I'm going to do in my code. And then once you find it, then I'll just write code to pull the fields that I'm interested in. Okay, moving along. I've shown you so much with this. And this is really, down to the coding example. And if you're on the, again, the Discord listening in, again, if you look at my notes right now for the slide titled reading underscore eProcess object, all the code is in the notes, and you can definitely try it out for yourself. I'm going to show a little bit here today, but I don't want to kill people